Okay, Dr. Matthew J. Trom here. We are going to do a tolerance loop example for the Burette. The Burette and the Stopcock. So what I'm interested in is this interface here between the rings on the stopcock itself, and the burette, right? So when I push the burette into the stopcock, there we go. There's an interference fit between the O-rings and the burette, right? The O-rings have to be compressed, and you can sort of see them being squished and compressed there in order to facilitate that seal. And so what we're going to do is try to figure out the tolerance loop that gives us the relationship between the minor diameter of the stopcock, the burette, and the O-rings. And we're going to do that by first taking a couple of measurements. So let me move these out of the way, and let me draw for you the picture so that we can get oriented. So here is the center line. There we go. And somewhere up above the center line, so we're now looking at the stopcock body itself, and here's the groove that the O-ring lives in, right? And then here I'm gonna draw the O-ring, and you know how terrible I am at freehand drawing circles. So there we go. Okay, so here's the O-ring, more or less. And then, as I mentioned, when you push the burette over the O-ring, these O-rings, they compress down. So when the burette gets pushed over the O-ring, there is some interference between the O-ring and the wall of the burette, right? So I'll draw it that way. The circle represents the uncompressed O-ring, and then the burette represents kind of the wall of the burette, which the O-ring will have to deform to accommodate when the burette gets pushed into place. So let me just sort of hatch this to indicate that it's a solid, and let me also hatch this down here. This is the stopcock to indicate that it is a solid, and the O-ring is also a solid, but I'm not going to hatch it because I think you get the idea. Okay, so here is the tolerance loop that I have in mind. So I'm going to start from the center line, and I'm going to first make a tolerance vector, which I'll call, let's call it S for stopcock, and that's going to go from the center line of the stopcock up to the minor diameter, that is the inside edge of this O-ring gland, which I'll show you in a second when we take the measurements, kind of what I'm talking about. And then that vector is going to have an uncertainty associated with it, so we represent that as this sort of little curly loop here. And then from that point, we're going to draw a tolerance loop that runs across the entire diameter of the O-ring. Okay, and we're just going to call that maybe D for diameter. And then it, of course, is going to have, let's just make a little extension line here. It's going to have a tolerance associated with it, so that's called delta D. And then we've got an interference, right? So this O-ring has to compress by a certain amount in order to accommodate the burette wall when it comes along. So we're going to have a vector that goes back in that direction, which we're going to call I. And we're going to have a little loop that we're going to call delta I. That's I for interference, and delta I for the uncertainty of that interference. And then ultimately, this is the inside diameter of the burette, and we're going to come all the way back down to the center line to complete our tolerance loop, right? And that must happen because tolerance loops are only effective when they end at the same place that they start, hence loop. And then there's the uncertainty in the burette inner diameter. So there's my tolerance loop, right? So it runs from the center line to the stopcock inner diameter, across the diameter of the O-ring, down a distance that's representative of the interference between the O-ring and the burette wall, and then ultimately all the way from the inner diameter of the burette wall all the way down back to the center line to complete the loop. Okay, now we need a couple of vectors, so I'm going to just use the names of the vectors that I called out here. So this is going to be vector S, this is going to be vector D, this is going to be vector I for interference, and this is going to be vector B for burette. And then, of course, I've got to measure those to figure out what they are. And so the way that I'm going to do this, I'm going to sort of start in the middle. And so we actually had a good debate about this in class. The diameter of the stopcock, let me try again. The diameter of the O-ring is not the relaxed diameter of the O-ring, but it's the diameter of the O-ring when the O-ring is stretched over over the stopcock. And let me kind of give you a sense of why that is. Okay, so when I've got the O-ring just sort of pulled off there, it's relaxed, and it's probably hard to see it, and there's really no way that I can measure it because the O-ring is very compliant. But if I give this a whirl here, let's zero this guy, and let's see if we can just get kind of a sense of maybe what this diameter is without compressing it too much. Okay, oh, that's too much. So I'm going to try not to compress it, but I'm going to try to get right to the point where I'm just barely holding it. Okay, so maybe something like 11.13 would be the diameter of the O-ring. It's something like that. The diameter of the O-ring if it's not stretched around the stopcock. Now, let me take the same measurement for the O-ring diameter when it is stretched out around the stopcock. Okay, and you can see there it's quite a bit bigger, right? It's about 2/10 of a millimeter bigger, and that's because again the O-ring is around the stopcock, and so the O-ring is already deformed to some extent because of being kind of stretched around the stopcock, and so it's actually that outer diameter that we want to use for well, at least our calculation for the diameter of the stopcock. So let's see, what do I get here? Okay, maybe about 11. Okay, 11.28. Okay, so let's keep that in mind. So let's just say the overall stopcock mounted ring diameter is let's see. What is it? 11.29 millimeters, and ultimately I'm going to need the radius. So I'm just going to call this R for the radius, and that's obviously going to be half of the diameter. And so let's see if I can come up with a value. So 11.29 divided by 2. Okay. Okay. So I'm calculating here 5.645 or so, but I've already done it, and I've put all of the numbers in, and so instead of saying 6.65, I'm going to say that this is 5.72, and again, the reason for that is because I've already done the math right here, and I'm using this example so that I don't have to crank through all the numbers so quickly, or so I can crank through the numbers quickly for you, and so we're going to use this 5.72. But you can see there's quite a bit of variability even in my own internal measurements of that value. Okay, so that's the radius from the center line to the edge of a O-ring that is sitting on the stopcock. Well, I've got this stopcock. The O-ring's off of the stopcock. Well, hey, that's probably my problem right there. I forgot to zero this guy. There we go. Okay, so let me get the minor diameter. So to show you guys, I'm actually inside that O-ring groove, and I've got here. Okay, about maybe let's try that again. Okay, 8.25. Okay, so minor stopcock diameter is 8.25 millimeters. And okay, so again, we'll call this a radius, and I'm going to say that that is equal to 4.105 millimeters. And again, this might not be entirely consistent. 8.25 divided by 2. Okay, right, it's very slightly off. And the reason, again, is I've already solved the problem right here, and these are the values that I took before. And so I want to be sure that I'm consistent all the way through and using values without having to spend a lot of time cranking through the math. So anyway, that's how I take those measurements. And as you can see, there's some uncertainty even in my own kind of internal calculations for those values. But these are the values that I'm gonna run with, because those are the ones that I used before for the analysis that I finished. Okay, so the next thing that I need to do then is start to fill in these guys. So I know S, right, because that is the radius of the stopcock. So let's replace this R with an S, just to be complete about it. Okay, and so this is going to be based on my measurement that I took before I started the video, 4.105 meters. And I don't know the uncertainties, delta S plus and delta S minus. I'm going to just use those as placeholders there. And this was just references caliper measured. Right, so I just pulled those values off my caliper. Okay, the next thing that I need is the burette inner diameter. So let me grab my burette. And let me make sure that this guy is zeroed. Okay, and then how to do this so you guys can see it. There we go. Okay. So that's how I measure the inner diameter of the burette. When I do it now, I'm getting something like 11.14 for that inner diameter, and so 11.14 is the burette inner diameter. And again, like before, I've actually measured all these in advance, and so I'm going to use the number. Let me just do the calculation here. 11.14. We'll see how close I got. Divided by 2, 5.57. Okay, so I ended up using burette. This is the radius of the burette is 5.585 millimeters. Again, not quite 5.57, but again, I've already solved the problem and cranked through all the numbers, and I know that it works. So I'm going to stick with the example that I've already done. Okay, so that value goes here, 5.585 millimeters. And I don't know those uncertainties either, so I'm going to call this uncertainty in B plus, and this is going to be uncertainty in B center line. And we're going to go, sort of some distance. Okay, some distance, there we go, some distance to the inside wall of the stopcock. This is the value that I've already measured, which is 4.105 millimeters. This guy is the value that I'm looking for, that's D, and then this value is the value that I measured again when I was looking at the outside diameter of the O-rings when they're sitting on the stopcock. So that's how I have that value. Remember, that guy is this value right here, this 5.72 millimeter radius. And so if I just take 5.72 and I subtract 4.105 millimeters, I get 1.615 millimeters, and that's my value for D, and I'm going to put that right in here. So 1.615 millimeters. Okay, and I don't know these uncertainties either. I don't know these tolerances, so I'm going to call this uncertainty and tolerance D plus and uncertainty and tolerance D minus. Okay, now the last thing that I need to figure out is I. I is the interference, and so to get the interference, I actually have to go to a O-ring handbook, and I looked up the fit for a static O-ring of this dimension according to the O-ring handbook, and what it tells me is that the interference has to be 0.08 millimeters, and on the plus side, I have a tolerance there of 0.0 let's see, 4, 5. And on the lower side, I have a tolerance of 0.055 millimeters. Okay, and this comes out of a Parker O-ring handbook for static seals. And the reference that I did here, this was caliper measured. And I'm going to just say see below, because remember, we didn't do this directly. We used a calculation to get at it. And this one, of course, this is B, which is the inner diameter of the stopcock, and so that's caliper measured. Okay, and so that is that's the setup for my tolerance loop. So I've got the loop here. I've got all my dimensions. I've got the tolerances that I don't know, the tolerances that I do know, the nominal dimensions, where they all came from, and I'm set to move on to the next step. Okay, so that let me pause here, give you guys a quick break, and then we will revisit and crank through the math in the next video. See you in a sec.